Today we're going to be interpreting exponential functions. So the first thing we're going to look at, we have two people. We have Lynn and Diego, and they're discussing two expressions, x squared and 2x. Lynn says that they think the two expressions are equivalent, and Diego says, I think the two expressions are only equal for some values of x. Do you agree with either of them? Explain or show your reasoning. So it could be the case that they're both correct, one's correct, or neither is correct, and we have to talk about that. So what does x squared actually mean? Well, x squared is the same thing as x times x. What does 2 to the x actually mean? That means that we're going to take 2 and multiply it by itself x times. So it's not necessarily just 4, but if x was 4, that would be 4 times. Okay, so it's x times. So let's look at their work for specific cases to try and disprove their information. So let's see if Lynn is correct or not correct. So if we use, let's say first, if x equals 5, okay, if x equals 5, then 5 squared would be 5 times 5, which is 25. Then 2 to the 5th, if we use that x, would mean that we're taking 2 and multiplying it by itself 5 times. And 2 times 2 times 2 times 2 times 2 is 32. Are these two things equal to each other? So those two things are not equal. That symbol means not equal. So Lynn is not correct. Okay, let's though look at Diego. Diego is saying sometimes. So can we figure out a number that would work in this situation? We know that it's not correct if x equals 5. So let's look at if x equals 4. So 4 squared is 4 times 4, or 16. 2 to the 4th is 2 times itself 4 times, and 2 times 2 times 2 times 2 is 16. Are those two things equal to each other? So yeah, so this is equal. So Diego is correct. Okay, Diego is correct with this. It doesn't happen for all of them because we disproved it. We found a counterexample here, but it does work for at least one value. So Diego is correct. All right, so let's take a look at a situation here. We have the cost in dollars to produce 1 watt of solar energy as a function of the number of years since 1977, and we're going to call that T. So from 1977 to 1987, the cost could be modeled by an exponential function f. And here is this graph. Okay, based on this graph, we're going to find a number of pieces of information down here. Okay, so it says, what is the statement f of 9 is about equal to 6 saying about this situation? Okay, f of 9 is about 6. Well, this 9 inside is the input. So what is that? That's on this x-axis here. So this says 9 years after 1977. That's when we started. So that year would be 1986. The output here, the cost of solar was, here's your output, that's in dollars, so $6 per watt. Okay, that's what it says here as our output. So what does f of 4 mean? Well, we don't have an equation for this, but we can go up to the graph. F of 4, that means that 4 years. So here we are at 4 years. That's the point we're looking at. So 4 years after 1977, which would be 1981, it was, let's see what that is. So what are we counting by here? We've got 1, 2, 3, 4 boxes until we get to 20. So that means that each space here we're counting by 5s. So if we're here at 4 years, we go up, we're across over here, we're 1 box above 20, so it would be $25 per watt. Okay, so that's what that number means in this context. So what about 3.5? So that means that 3.5 years, or 3.5 years after our starting year of 1977. So 3.5 years. Okay, what are we counting by here? So we have 2, and then there's 4 boxes to get to 4. So this would be 3 years, halfway in between them. So we're looking here at 3.5 years. This is the point about where we're looking. So we're 2 boxes above 20. Since these are counting by 5s, this would be $30 a watt. Okay, that would be $30 a watt. Okay. Next question says, when f of t equals 45, what is t? So in these previous questions, we had an input. We knew how many years it happened. We were trying to find what the dollar watt was, the output. Now they're giving us the output of 45. So we need to figure out where 45 is on this y-axis. So as I'm going up here, remember you're counting by 5s. Here's 45 right here. So we're going to follow that across until we get to this point. This point, following it down, we know that t equals 2. Okay? That's the x-coordinate of that, or the input value of that point. So what does that value of t represent in the context? Well, this is our years since 1977. So we would say 2 years after 1977, which would be 1979, solar cost the $45 a watt that they told us. So they gave us the output, you have to find the input. All right, so the last question down here is saying by what factor did the cost of solar cells change each year? So we're looking at what happened from one year to the next, how much we have left out of how much already was there. So if we had after 1 year, it was 60, and we started with 80 watts, that would simplify to the fraction 3/4. That's what happened from year 1 to the beginning, to the initial amount. So what happened from year 1 to year 2? Well, in year 2, we already said that we had 45 out of the 60, which also simplifies to be 3/4. Let's look at one more. So if we have year 4 here that they gave us, that we already came up with was, well, we could even do, 25 out of the previous one that they gave us. Oh, I guess I jumped over this one here. But this was about 34. That's also going to be 3/4. So it doesn't matter which ones you look at. You could look at any of these and compare 1 year to the next and see what happens, but they all should give you 3/4. That's what factor it changed. Okay? All right, the next thing we're going to look at is paper folding and how this can actually be a model by exponential growth as well. So, and actually exponential decay. The thickness T in millimeters of a folded sheet of paper after it's folded n times is given by the equation here. Okay? And what does this number 0.05 represent right there? Well, since that's our starting amount, that's going to be the thickness of a sheet of paper before we fold it. okay? Before we fold it, we would end up with that, okay? So if we're looking at graphing this, so let me try and pull up here. My Desmos. So if we have 0.05 times 2 to the x power, and we have this graphed, okay? It says how many folds does it take for the folded sheet of paper to be more than 1 millimeter thick. So you can either look at what's happening here. So we're looking at our graph. You can also make a table, but if we're looking at 1 millimeter, this is our thickness here. We're looking for where it goes above this 1. Well, it's going to go above the 1. 4 folds isn't quite there, so it would be 5 folds. And explain how you know. Well, that's where you're just looking at the graph and you're seeing where it happens. Okay? You're seeing where it happens there. All right. So moving on, the area of a folded sheet of paper is 93.5 square inches. Find the remaining visible area of the sheet of paper after it's folded in half once, twice, 3 times. So let's make a table of information for this. Okay? N is going to be the number of times it was folded, and A is going to be the area. So after 0 times of folding it, our area was 93.5. They told us that. If we fold it once, what happens to the area of that piece of paper? Well, it's going to cut in half. So we would have 46. Let me rewrite this again. 46.75 would be the area of that piece of paper, the visible part of the piece of paper now. If we fold it again, the area is going to cut in half again. So we would have 23.375. And if we fold that piece of paper one last time, we're cutting that area in half. So we would have 11.6875 square inches. Okay? So it says write an equation expressing the visible area A of the sheet of paper in terms of the number of times it's been folded. Well, A is our area, and they're using lowercase a here. What was our initial amount? That was 93.5. What happened each time as we went along this chart? What did we do each time with that area every time you fold it? It gets cut in half. Well, we have half of the visible area remaining if we get rid of half of it. So this is going to be our decay factor, and we're taking that to the n power because we're folding it. Okay, so we're going to really quickly here look at our graph of this as well. So we have 93.5 times, I'm going to use 0.5 to the n power, you can, or to the x power. You can kind of do whatever you want there in terms of 1/2 or, so here's our graph, 1/2 or 0.5. In this context, can n take negative values? Can you fold the paper negatively? So I guess we'll say maybe if you add more paper, or if it was already folded to begin with. But the bigger thing is, can A take negative values? Can your area be negative? No. Okay, your visible area can't be less than 1. And that's it.